Good morning. So this video presentation keeps on going with the first part where we already showed how we can calculate the formula of magnesium oxide by experiment. Now this is doing it the other way around. In the first part where we discussed how we can find that the formula is MgO by experiment and not by valency, we were oxidizing a metal, so we were adding oxygen to a metal, or adding oxygen to the magnesium to form the oxide, magnesium oxide. Now we're going to do it the other way around. We are going to react copper to oxide with hydrogen, and we shall reduce the oxide, that is, remove the oxygen from the oxide to give the pure metal. So, in other words, I can write the chemical equation right here at the start. We shall be dealing with this chemical equation. We will start off with copper 2 oxide, solid, which as you should know is a black solid. We shall reduce that using a stream of hydrogen gas. So as a state symbol we put in G. The reaction is moving forward to give copper solid, which is a pink transition metal, and the side product is water vapor. Now, since this reaction involves heat, it is correct to write the state symbol of the water as G, unless it has condensed to form moisture. Let's check out the balancing. Okay, so we've got 2 hydrogens on the left, we've got 2 hydrogens on the right, 1 oxygen on the left, another oxygen on the right, 1 copper on the left, and another copper on the right. The reaction is balanced with respect to atoms. So basically what we shall be doing is we shall be looking at the initial mass of the copper 2 oxide. And note that since copper 2 oxide is reacting with hydrogen, the oxygen is being removed. So a first prediction, even before we start the experiment, is that if we have, for example, 3 grams of copper 2 oxide starting out, the end mass after I have reacted the copper 2 oxide with the hydrogen should be less than 3. Why? Because the oxygen from the copper 2 oxide has been removed. It has reacted with the hydrogen, leaving the copper metal. And logically, copper metal with the oxygen gone will weigh less than the initial copper 2 oxide. Let's now move on to the learning outcomes that I have listed in the next slide. The learning outcomes for this presentation are very, very similar to the one where we reacted magnesium with oxygen in order to determine that the formula is magnesium oxide. Actually, they are pretty much the same. You will use a mole calculation, a simple mole calculation also in this presentation in order to find the chemical formula by experiment. Okay, so we shall be determining that the chemical formula of copper 2 oxide is CuO without reverting to the use of valencies. Okay, we should, however, be able to describe the experimental procedure. So what this presentation does is it focuses on the methodology, on how it is done, on how this would be carried out in the lab. And the climax, if you like, of the presentation is reached at the end of the presentation, where there is a really good video demonstration presented by the Royal Society of Chemistry. The demonstrator is performing the reduction of copper 2 oxide in a school which is associated with the Royal Society of Chemistry. I believe it is Warwick School. Good. Now, but I will go into further detail about that presentation, about that video demonstration, just one slide before I will be ready to show it. Next, so we shall be finding the formula of copper 2 oxide. Notice that at ordinary level we are only interested in simple binary compounds. A simple binary compound is one such as copper 2 oxide. We call it a simple binary compound because it contains only two elements. Okay, we have the cation, which is the copper ion, and we have the oxide anion. Remember that copper 2 oxide is an ionic solid, so realistically speaking, really what it really contains is a Cu2 plus cation, a positive ion, and an oxide anion. Okay? Now, the formula as displayed shows us that the mole ratio, the number ratio of the atoms is 1:1. But we know that via valency. What we're going to do is we're going to prove that formula by means of experiment. Finally, we shall be defining empirical formula. Once again, we have already defined it. We have also seen the difference between the empirical and molecular formula. I gave in the previous presentation the difference between CH2O and C6H12O6. CH2O being the empirical formula of a monosaccharide sugar, and C6H12O6 being the molecular formula of a monosaccharide sugar. Those of you who do study biology should definitely be familiar with this terminology. Those of you who don't, well, they are familiar at this point. Let's now move on to the next slide, where I shall start discussing the procedure of how to reduce copper 2 oxide in a stream of hydrogen, as it is also shown in the final demonstration by the demonstrator at Warwick School. The apparatus that we use is based around our reduction tube. Now, the reduction tube is this Pyrex tube. Do know that Pyrex is a special form of glass that, as you know also from your kitchenware, can resist very high temperatures, several hundreds of degrees Celsius. Good Pyrex can be rated up to 500 to 600 Celsius, okay, without risking a crack. Now, do note that the reduction tube is a special design of tube because right over here it's got a little nozzle. This is an exhaust nozzle where excess hydrogen, which does not react with the copper 2 oxide, can escape. Now basically the idea is this. First of all, in these bullets over here I've just listed the equipment. So you've got the reduction tube, which I've already outlined. Do know that you also have a rubber bung, okay, which is a single hole, as you can see. It's a perforated single hole rubber bung, okay. Now, although it's not indicated, where you've got gas supply, you do have rubber tubing, okay, and connected to the rubber tubing there is a hydrogen gas cylinder, okay. Now, the hydrogen gas cylinder, as we shall also see from the video demonstration, has its own open valve, on-off valve, which is connected in turn to a pressure regulator, and then there is a flow gas regulator, a gas flow regulator, which controls the flow of gas into the reduction tube. So it's very important that the hydrogen gas which is entering the reduction tube is at reduced pressure. Typically it would be reduced to atmospheric pressure, to room temperature pressure. Excuse me. Although they are not indicated, the reduction tube is held in position using your normal burette stand, the boss, and the clamp. Okay, the boss is the fitting that connects the clamp to the burette stand. I used to call it, in my time, we used to call it a boss head. Okay, it's what you use to tighten around your burette stand, and at the same time it tightens around your clamp so that you can hold, for example, a burette in position above a conical flask. In this case, it's going to use the clamp in order to hold in position your reduction tube. Also, although it is not shown in this diagram, you will need a top pan balance that will measure masses to the nearest 0.01 of a gram, 1 all over 100 of a gram. We need that level of accuracy in order to determine the empirical formula of copper 2 oxide accurately enough. Now let's go on to the next slide where we start describing the procedure itself. The first step is, as indicated in your chemicals, section over here, you will need to weigh out about 3 grams of copper 2 oxide. Remember that copper 2 oxide is a black oxide, that should be that way. You should have your copper 2 indicated at all times. Notice that we will need AR grade. AR is an abbreviation for analytical grade, and it is very different from GPR grade. The GPR grade is general purpose reagent. The reason for using AR grade is that AR grade copper 2 oxide will have much less copper contaminating, if you like, the composition. It is a very, very pure sample of copper 2 oxide, and this will give the best result that could be achieved in a school lab when it comes to determining the chemical formula, the empirical formula of copper 2 oxide by experiment. As you shall see in the video demonstration, you will also need a hydrogen cylinder with valve gear. The valve gear I've already gone into. You will need a pressure regulator, just like the pressure regulator that you use at home with your liquid gas cylinders. The idea is the same. Of course, the type of regulator will be different. And of course, there will need to be a gas flow regulator as well after the pressure regulator. So the idea is to strongly heat the copper 2 oxide, which is dispersed. Notice that it is dispersed at the center of the hard glass tube. It is spread out. It is positioned well away from the outlet where you have the hydrogen being vented off and burnt off. The reason is that since you are going to be heating very strongly and there is going to be the hydrogen airflow, this would tend to agitate your copper 2 oxide, which remember is a fine powder, and it could result in losses of copper 2 oxide via the vent. That you want to avoid, otherwise your calculation of the formula of copper 2 oxide will prove incorrect due to loss of compound. Let's now move on to the next slide. As you can see, once again, we've got the apparatus which is set up at the bottom, but now we're going to go into the detail of each step. Going through every step as it actually has to take place. First of all, the copper 2 oxide that we shall be using has to be dried. Otherwise, any water moisture will lead to a false result when we come to calculating the copper 2 oxide formula as CuO, remember. The copper is dried out typically in an oven at 100 Celsius. I would say it is heated for around half an hour. It is stored in a desiccator. A desiccator basically is a sealed container, containing a desiccant such as silica gel that will keep your copper 2 oxide dry until the time that you need to use it. Now, the steps are indicated over here. So step number 1 is weighing the reduction tube empty, without any copper 2 oxide in it, The next step would be to place about 3 grams of copper 2 oxide. Now note, the word is about. It doesn't have to be exactly 3 grams. The point is that you are going to weigh about 3 grams, but whatever the mass you take, that has to be recorded very accurately. So typically I would weigh out 2 point, for example, I'm giving an example, 95 grams. It is about 3 grams, but it is exactly 2.95. The exact mass close to 3 grams has to be noted. You could measure a mass a bit below 3 or a bit above 3. Why 3? It's a good point to carry out such a reduction experiment just using this sort of little tube. So the copper 2 oxide should be spread out over a length of about 4 centimeters. It should be centered, okay, in the middle of the tube. And the reason is that you should do this to keep it away from the nozzle over there, from the exit point where the hydrogen will be vented, so that it will not be agitated so much to be lost. Remember, it's going to be strongly heated from beneath, okay? You're going to have a gas flow in this direction of hydrogen, so under the influence of the gas flow of hydrogen and the heat from beneath, the powder, which is a very light powder, tends to get easily agitated. We don't want any of it to be carried over into the venting valve, and this would cause a loss of compound, which would cause a problem with our calculation of the formula of copper 2 oxide. You would then, after adding your 2.95 grams of copper 2 oxide, you would reweigh the hard glass tube, and it would this time contain the copper 2 oxide inside it. Once you've weighed the hard glass tube with the copper 2 oxide inside it and recorded the data, as you will see, not in the next slide, in the slide after, where I have presented a sample calculation, okay, you will clamp the reduction tube, okay, so it is clamped at its open end, okay, and it is connected to the bung, the glass tube, and the hydrogen cylinder. At this point, the gas flow is turned on and it is adjusted to a gentle flow, as you will see also from the video demonstration. The demonstrator, once he's got the flow of the hydrogen on, he checks the flow rate by putting the nozzle towards his cheek, okay? So before connecting up with the hard glass tube, he checks the rubber tubing, okay, for correct flow by putting up the end of the rubber tubing against his cheek and ensuring that the flow is not too much. Let's now move on to the next slide. The first step is to light the Bunsen burner and ensure that it's on the full open air hole so that we get a roaring flame. The roaring flame will ensure a high enough temperature for the oxide, okay, so the oxide is this sample over here, to be completely reduced to the copper metal. So basically, you've got the Bunsen burner on, but the first thing to do, even before starting heating, is to ensure that you have hydrogen traveling through the tube. Okay, so before you start heating, okay, you open the gas supply of hydrogen at the correct flow rate and you flush out any air which is contained within your reduction tube. The demonstrator, I believe, does it for about a minute. So you will pass hydrogen gas for about a minute before heating. Okay, this will drive out any air inside the tube, and then what you do is you ignite the hydrogen at the end. Okay, the hydrogen over here is ignited. This ensures that any hydrogen which is in excess does not cause an explosion risk, but it is immediately removed in that way. Okay, so you are removing the hazard by igniting it at the exit point. So once you have the hydrogen flow moving through the cool glass tube, okay, that is the point when you start to heat strongly. At that point, the copper 2 oxide, because of the very strong heat, will start to react with the hydrogen that is passing over the surface of the oxide metal. At the high temperature, at the high Bunsen temperature, the copper 2 oxide is reduced to copper metal, and you will see this. The demonstrator describes how within less than a minute, okay, the copper 2 oxide will change from a black compound to a pink metal, okay? Now, he also explains that the correct procedure is not to just stop heating as soon as all of the copper metal appears pink, but to keep on heating for a further minute to ensure that any unreacted copper in your unreacted copper 2 oxide will actually be reduced to copper. It is very important to remove the flame after the reaction appears to be complete, but to keep on passing hydrogen through the tube until it cools down. And the reason is this: if I stop the flow of hydrogen, okay, there is a risk that you would have air inside the tube, air could enter inside the tube, it would react with the very hot copper, and it will convert back some of the copper to copper 2 oxide, and you'd have to start over again. So the idea is this: first remove the heat, then at the same time ensure that your hydrogen keeps on flowing. It keeps on flowing till the tube, the hard glass tube, is cool enough to touch comfortably. At that point, you can close off the hydrogen flow and reweigh the contents and the hard glass tube. Okay, so the contents can be weighed inside the hard glass tube, and the final mass of the hard glass tube and the copper metal should then be noted. Let's now move on to the next slide. In this slide, we shall look at some typical results also, so that you get a feel of the data. Okay, so the first thing to check out is the first line over here. We have the mass of the empty reduction tube. That's the hard glass tube with a special nozzle, as we said. So typically that would be around 20 grams. Next, we have the mass of the copper 2 oxide. We said 3 grams, so there you have it. So 20 plus 3, that's 23 grams. So it's very clear that the mass of the copper 2 oxide is 3 grams. That is the starting mass of our sample of compound. Then, after heating, notice the mass of the cooled reduction tube. So the reduction tube, as I explained in the previous slide, has been allowed to cool, okay? And the copper content after heating. Well, as we explained also, after the copper 2 oxide has been heated strongly in a stream of hydrogen, it has been reduced to the copper metal. And this is why you have copper content after heating, okay? So notice that the mass of the tube and the copper weigh less than the mass of the tube and the copper 2 oxide. The loss in mass, the difference, must be due to the oxygen that has reacted with the hydrogen, okay? The oxygen that has reacted with the hydrogen will cause this decrease in mass. So the mass of the copper formed after heating the copper 2 oxide with hydrogen is 2.4 grams, and the mass of the oxygen is 0.6 grams. Notice that we now know quantitatively the mass of copper in the copper 2 oxide and also the mass of oxygen in the copper 2 oxide sample, and I have listed them again over here in this table to further clarify. As we did with magnesium oxide, in order to calculate the correct formula, we need to convert mass into moles. Moles are numbers. Numbers can be expressed as a ratio, which is why we need to convert from mass into moles. And what you do is, as we did with magnesium oxide, so for example, if we look at copper and we have 2.4 grams, we would say, I can write this to help you out, 1 mole of copper, okay, it will take me a bit of time, okay, because I do not have a pen to do this with. So 1 mole of copper will weigh 63.5 grams, okay, but we do not have 63.5 grams. All we have is 2.4 grams. So by simple proportion, you will find that 2.4 grams is equal to 0.038 moles, because by simple proportion you have 2.4, okay, all over 63.5 of 1 mole, okay? Since 1 mole is 63.5 grams, 2.4 is much less, and it works out to be 0.038 of a mole. Likewise, you calculate for oxygen. You know that 1 mole of oxygen atoms weigh 16 grams, but we do not have 16 grams of oxygen. All we have is 0.6 grams. So how many moles is that? And clearly also by simple proportion, that will work out to be 0.6. Okay, I'll keep on writing on this slide in the available space. 0.6 on 16 works out to be also 0.038 moles. So it's very interesting to note that after I have changed over the masses of copper and of oxygen into moles, the moles are equivalent, which is exactly what you should expect. Since they are equivalent, okay, the mole ratio is 1:1, and therefore the formula is written as CuO. CuO means that the ratio of the atoms is 1:1, and it is the same ratio that is obtained when you use valency. As you know, copper has a valency of 2, oxygen has a valency of 2, therefore the resulting compound has the formula copper 2 oxide CuO. Notice that by experiment we have obtained the exact same formula that you would obtain via valency. Now, when watching the video presentation, there are some points that I have taken that I wanted to alert you about. The first thing to note is that the demonstrator does not initially refer to copper 2 oxide as copper 2 oxide, but rather as copper oxide. Watch this. It is always even emphasized by MedSec to refer to compounds that include metals with variable valency and to specify their valency. So for example, if I have CuO, it's copper 2 oxide. Why? Because if I had Cu subscript 2O, that would be copper 1 oxide. So specifying the valency will specify the type of compound that I've got. Now, when watching the video demonstration, you should watch out for water droplets forming inside the reduction tube. Why do water droplets form inside the reduction tube? Well, very briefly, I already explained this on the first slide. Remember that copper 2 oxide is being reduced by hydrogen. When it is being reduced by hydrogen, what's happening is that the oxygen in the copper 2 oxide is reacting with the hydrogen, and the product, I'm not going to write the balanced equation, I'm just going to remind you why you will expect to see water droplets. You will therefore get water vapor forming at high temperature, but of course, there are parts of the tube that are away from the flame where the hot water vapor, if you like, can condense, and it could form a moisture film, a fine droplets, okay? As you keep on heating, those droplets will be removed. So that's the first point to note. Also, initially, okay, before you start heating, okay, as we said, you have to pass the hydrogen through the cold reduction tube, and as soon as you ignite the hydrogen that is being exhausted through the nozzle, you will notice that the flame is pretty high. However, when you start reacting the copper 2 oxide inside the reduction tube with the hydrogen, when you start heating the sample of copper 2 oxide, you will notice that the flame suddenly starts to drop. And the reason is this, that some of the hydrogen that is entering the tube is going to start reacting with the copper 2 oxide. So it's as if you have reduced the loss of hydrogen to the atmosphere. Since you have reduced the loss of hydrogen to air, there is less hydrogen available at the exit nozzle to burn, and since there is less hydrogen available to burn, the flame height will also drop. Also, at times, the flame, at the exit nozzle can be colored green, and the reason is that since you are heating copper 2 oxide to a high temperature, some of the copper could be atomized, and the flame test for copper is a greenish blue color. So basically, atomized copper atoms are taking on that coloration. The fourth point to note is that it takes approximately 1 minute for the surface color of the black copper 2 oxide to change to pink. However, this does not mean, as the demonstrator explains, that you stop heating there, because there is some unreacted copper 2 oxide beneath the surface that still needs to be converted. So you keep on heating, typically for a further minute or so, to ensure that all the copper 2 oxide has reacted and all of the moisture has had time to be removed. It's very important to stop heating, but to allow hydrogen to keep on flowing through the tube until it is cool enough to hold, And the reason, as I already explained, is to prevent the reduced copper metal from reacting once more with any oxygen that might enter your reduction tube. Now, do take time to watch the video. The video is really an excellent video. It is organized and, if you like, coordinated by the Royal Society of Chemistry in collaboration with Warwick School. And the demonstrator does a very fine job of really clearly showing you how to do the experiment. Thank you for watching this lesson. Now go on to watch the video in the next slide.